Hello, everyone. This is Professor Ma, and this is a short introduction some of the sections on double integrals. We have we had the Calaveri's principle, basically saying if the cross length of two shapes are the same, then have the same area. And similarly for solids, if the cross-sectional areas are the same, then the two volumes of the two solids are the same. Basically, just I can view this as a one volume, and the other one is gonna got kind of topple over on the side a little bit. Or another way to think of this is these volumes are stacked together with very thin disks, and I can reshape those disks outline differently, but the volume of the solid doesn't change. And so the in math, so in terms of integral, then we say the area is integral of cross-sectional length. Area is the integral of length, and the volume is the integral of cross-sectional surfaces. So if I have a formula that defines some rectangular things, and let's assume it's positive. So it has a picture. Let's assume it looks like that. So if I want to calculate the volume, then I can integrate these cross-sectional area across X. So in this picture, so as X change from A to B, I calculate the, if I can find the cross-sectional areas along X, along from X to A to B, then this will be the volume. But if I were to look at this A of X, this area, it goes from C to D along the y-axis, this is Z, and so its area is equal to the integral of the C to D of f of xy So I can put the formula for cross-sectional area for A of X into this double integral form. And we call this the iterated integral, iterated integrals. And there are two ways to set it. I can set these to be the integral of cross-sectional A of X, or I can do a slice it the other way, as cross-sectional as integral A of Y's. Okay, so I can do it this way. Then in these manners, I will be, the double integral will be written in these fashions. Okay, because this is the area of that. Okay, so this, I got this two iterated form, depends on which way you view the cross-sectional area. Then there's a third way of doing computing volume. That is by the fundamental theorem of calculus. What we do is we take the rectangular domain and we chop it into a small rectangular pieces, and then we look at how much volume is on top of each subrectangle. And we can approximate that by taking a point inside that subrectangle and evaluate how high it is. Of course, how high it is, let's say this is Z of I, we say is equal to f of xi yi. And then then the volume is going to of this piece, and I'm going to call it V of I. It's approximately Z of I, the height, times the area of this little rectangle. AOI. So that's what this is about. And I'm going to add all those V of i's together for each subrectangle. And then I'm going to take the area become smaller, the region, the rectangular boxes area, subrectangle, each area I'm going to let it go, becomes smaller and smaller, it goes to 0. If the limit exists, then I call that limit the volume. Okay? And this, what we got, we write it in this manner. And notice we say this is differential with respect to A, where A is the area of a subrectangle. Okay. And then the following theorem says, oh, all 3 of them are the same. What? The iterated integral, the volumes, this is the dA. This is use sum of VI, and I saw area of as area of AI goes to 0, the subrectangle, and this of course is doable by Calaveri principle. Okay, integral of cross-sectional surface is the volume, and this theorem says if you calculate with the function z, a continuous function over a rectangle, then these are the same. Okay. So let's do some examples. And here's a function. And it's defined over the rectangle 1, 2, 2, 3. So it's this little column with a slanted top, and we want to calculate the volume of this column. So we do double integrals, and you can set the integral limit. You can do it either respect to y. This is going to be a of x. Okay. And after we integrate this definite integral, we get a formula in x. Keep doing. We get this formula in x. Then we integrate this with respect to x. Now we get the answers for the volumes. Okay. You can check if you do it the other way around, switch the numbers around, because the domain is a rectangle, so we can do this. Okay. Later on, we cannot do this. So this is very strict. It's because we can switch the integration because the domain itself is a rectangle. The next sections, we're going to do the general ones, and this is not allowed. But in here, we can switch, and actually we get the same answer. Then here's another examples of calculations, and we can go through the calculations. And next sections, like as I said, we will change the restriction that domain has a rectangle. We're going to do over kind of like arbitrary boundaries with some information about a boundary. Then how do we write these analogous volumes of a function's surface over this space. Okay, that's for next sections, and that's it. Bye bye. Have a good day.